Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Have you ever wondered what it would be like to move something just by thinking about it? No voice commands, no buttons, no controllers, just your thoughts, instantly turning into actions. That idea used to sound like pure science fiction. But today, scientists and engineers are literally connecting the human brain to computers to make it real. I'm Drew, and this episode is about brain chips, or, more accurately, brain-computer interfaces. These are devices that can read the electrical signals your brain produces, translate them into digital commands, and sometimes even send information back into your brain. They're one of the most ambitious technologies ever built, sitting right at the intersection of neuroscience, computers, and biology. To understand what makes this so powerful, let's start with what your brain is actually doing. Every thought, every movement, every sensation begins as a pattern of electrical signals sent between billions of neurons. Each neuron fires tiny voltage spikes, action potentials that carry information. When you think about lifting your hand, those spikes fire in a specific pattern that muscles interpret as lift up your hand. Brain chips have the potential to detect those signals, decode the pattern, and send it to an external device, like a robotic arm or a computer cursor. In a sense, they're translators between biology and technology. But that's only part of the story. Behind every working brain chip are years of experiments, micro-scale engineering, and algorithms trained to recognize the subtle patterns of thought. Over the next 20 minutes, we'll break down how these devices actually work, how close we are to practical use, and what happens when the line between mind and machine begins to blur. Before we can understand how brain chips work, we need to understand what they're listening to. Every thought you have, whether it's solving a math problem, remembering a song, or planning to move your arm, is encoded as electrical activity between neurons. These neurons don't just fire randomly. Each one connects to thousands of others, forming an incredibly complex web of communication. Together, they generate rhythmic pulses, like the coordinated patterns of a symphony. At the smallest scale, it all starts with action potentials. These are the tiny voltage spikes that occur when a neuron sends a signal. When enough of them fire together, they produce recognizable patterns that correspond to thoughts or movements. For example, neurons in your motor cortex fire in specific arrangements when you think about moving your hand to the right versus the left. Brain chips rely on these differences, on recognizing which patterns mean move up, move down, or click on a mouse. But decoding these signals is not simple. Imagine trying to understand a conversation between billions of people talking at once. It's what scientists face when they record brain activity. The electrical signals are faint, noisy, and constantly changing. To make sense of them, researchers use electrode arrays, grids of microscopic sensors that can detect the electrical field produced by nearby neurons. Each electrode records signals from one or a few cells, giving us a small window into what the brain is doing. When combined across hundreds or thousands of electrodes, that data starts to form a picture. Machine learning algorithms process the patterns, searching for correlations between specific neural activity and real-world actions. Over time, the software learns what kind of neural signals correspond to certain commands. This process, called neural decoding, is what makes brain chips intelligent. The chip isn't just reading electrical noise, it's interpreting meaning from it. Some brain chips take this even further. Instead of just listening to the brain, they can also send signals back. These are called bidirectional interfaces. Imagine a person who lost their sense of touch using a robotic hand controlled by their mind. A bidirectional brain chip could send artificial sensory feedback from that robotic hand back into their brain, allowing them to feel pressure or texture again. That two-way communication is what makes the technology so promising for prosthetics and rehabilitation. The most advanced research in this field often happens in animals first. Then, it gradually moves to human trials. For example, scientists have trained monkeys to control robotic arms using only brain signals, reaching out and grasping objects in real time. Similar experiments with paralyzed patients have shown that brain chips can restore a remarkable level of independence, from moving a computer cursor to even typing words through thought alone. All of this depends on precision, both in the neuroscience and in the engineering. The brain's signals are measured in microvolts, which is a millionth of a volt. The electrodes that detect them must be thinner than a human hair, flexible enough to not damage human tissue, and stable enough to last for years. That's where modern materials science comes in. Innovations like graphene, biocompatible polymers, and ultrafine gold conductors have made it possible to build electrodes so they can safely interface with living brain tissue. So when we're talking about brain chips, we're really talking about a fusion of three disciplines: neuroscience, materials science, and data science. The neurons produce the signals, the chip captures them, and then algorithms work to make sense of them. Together, they bridge the gap between thought and technology. Understanding the science behind brain signals is only half the story, though. The other half is the hardware, the physical technology that connects living neurons to a computer. Building a brain chip isn't just about packing sensors into a circuit. It's about making electronics that can survive inside the human body while recording signals that are 1,000,000 times smaller than what a phone microphone detects. At its core, a brain chip is made of three main parts: electrodes, signal processors, and transmission systems. The electrodes are what actually touch or come close to the brain's surface. They act like antennas, picking up the faint electrical fields produced when neurons fire. Traditional electrodes are made from metals like platinum and gold, but newer versions use materials like carbon nanotubes or graphene. These materials are lighter, more flexible, and less likely to cause inflammation, which is one of the biggest long-term challenges of brain implants. Next comes the amplification and signal processing stage. The voltages coming from neurons are incredibly weak, typically tens to hundreds of microvolts. That's not even enough to register on a standard circuit. So the chip has to boost the signal while filtering out noise from other neurons and from the body itself. This is done with analog amplifiers and custom-built microchips that sit right next to the electrodes. In a sense, it's like placing a sound engineer right beside each neuron, carefully tuning the gain so that the true signal stands out from the background static. Once the signal is amplified and digitized, it needs to be transmitted out of the body. Early brain interfaces used wires that physically connected the implant to a computer. Those worked well for experiments, but weren't too practical for everyday use. The risk of infection and mechanical strain was too high. Modern systems use wireless data transmission, often through low-power radio or infrared signals. For example, Neuralink's N1 implant, currently in early human trials, uses a sealed wireless module about the size of a coin that sits beneath the skull and transmits brain data without any visible connectors. Synchron, another company developing neural interfaces, uses a stent-like device that's inserted through the blood vessels, allowing a chip to sit inside the brain's vascular system without open surgery. Powering these systems is another challenge. Of course, the brain chip needs energy to run, but it can't rely on big batteries or cords. Most modern designs use inductive charging, similar to phone wireless chargers. Energy is sent through the skin using electromagnetic fields and collected by coils inside the implant. It's efficient, silent, and safe, as long as the heat produced stays below biological limits. The entire system must also be biocompatible, meaning it won't be rejected or cause scarring in the brain. The tissue around the electrodes can react to foreign objects by forming a protective barrier, which gradually weakens the signal quality. To counter that, researchers use flexible materials to move within the brain's natural motion and coatings that prevent immune response. The goal is to make the implant feel invisible to the body, something that can stay in place for decades without causing harm. Finally, all the raw data gathered from the electrodes must be handled intelligently. Even a small array can produce gigabytes of neural data every second, So the chip doesn't just record, it compresses and pre-processes information before sending it out. This is where on-chip machine learning comes in. Tiny embedded algorithms that identify meaningful patterns in real time, reducing the amount of data that needs to be transmitted. There's the result of a device that sits at the boundary of biology and computing, balancing fragility and precision. Building one that works reliably isn't just an engineering challenge, it's a test of how far human design can go while coexisting with living tissues. When you think of a brain chip, it's easy to imagine that once it's connected, it just reads your mind. But the reality is far more complicated. The chip doesn't actually understand thoughts, it records electrical signals from groups of neurons. The real magic happens afterwards, when algorithms translate those signals into something meaningful. Each neuron fires electrical pulses called action potentials, which only last a few thousandths of a second. A single thought, movement, or sensation involves millions of these spikes across different brain regions. The challenge is that the implant only records a tiny fraction of them. For example, a modern brain-computer interface might only track a few hundred neurons, while the brain has 86 billion. So decoding intent from this small sample requires powerful pattern recognition. Here's how that works. When a user thinks about moving their hand, certain motor neurons in the brain's motor cortex fire in recognizable patterns. The chip captures the voltage spikes from those neurons and sends the data to a computer, where software looks for correlations between those spikes and the movement the person is trying to make. This is known as neural decoding. Early systems relied on simple math models that mapped firing rates to movements. For instance, certain neurons fired faster when a subject imagined moving right. The algorithm worked to associate that pattern with the command, move right. Over time, with repeated calibration, the model could predict motion based on the neural signal alone. These early systems were accurate enough to let paralyzed patients control robotic arms or cursors, but they required constant tuning. Today's brain-computer interfaces use machine learning and deep neural networks to handle this decoding automatically. Instead of manually mapping every signal, the system trains itself on data collected while the user imagines or performs actions. Over many sessions, the AI learns which combinations of neural spikes correspond to which intentions, similar to how a voice assistant learns to recognize a person's speech patterns. Once trained, it can interpret new signals instantly. One of the key techniques used is spike sorting, identifying which neuron each electrical signal came from. Since electrodes pick up signals from multiple cells nearby, algorithms must separate overlapping spikes based on shape, timing, and amplitude. This is done with clustering methods, often powered by convolutional neural networks. The cleaner the separation, the more accurate the decoding. But decoding isn't just one way. In many systems, the computer sends information back to the brain, a process known as closed-loop feedback. For instance, when controlling a robotic arm, the user needs to feel how hard it's gripping something. Engineers can simulate that feedback by simulating sensory areas of the brain, closing the loop between action and sensation. This allows users to adapt naturally, just as they would with their own limbs. Companies like Neuralink, Blackrock Neurotech, and Paralyzed are building on these principles. Neuralink's chips process thousands of channels simultaneously and use AI models to predict intended motion in real time. Blackrock's Utah array, already used in human trials, allows paralyzed patients to type or play simple video games using only thought. Paralyzed, meanwhile, is developing high-end bandwidth interfaces that could transmit more neural data than any current system, enabling richer communication between the brain and machines. The long-term goal is to make these algorithms adaptive, to learn not just from neural patterns, but from context. Imagine a system that doesn't just move a cursor when you think about it, but knows when you're concentrating, frustrated, or tired. By combining neural decoding with contextual AI, brain chips could someday respond with an almost human level of intuition. It's important to remember that no system actually reads thoughts in the way that science fiction suggests. The technology interprets intent, not abstract ideas or private memories. But even with that limitation, decoding neural signals has already transformed what's possible for people with paralysis or sensory loss. The boundary between thinking and doing is becoming thinner, and the line between biology and computation is blurring faster than ever. The first and most powerful use of brain chips has always been medical restoration, giving back the lost abilities that once seemed impossible to recover. For decades, brain-computer interfaces have been used to restore movement, communication, and even sensation in patients with severe paralysis. One of the best-known examples comes from the BrainGate Research Consortium, which began clinical trials in the early 2000s. Using a small array of electrodes implanted in the motor cortex, participants who were paralyzed from the neck down learned to control a robotic arm simply by thinking about movement. The system converted their brain signals into commands for the arm, allowing them to reach, grasp, and even drink from a cup for the first time in years. More recent iterations of BrainGate's technology have enabled participants to move computer cursors, type on virtual keyboards, and interact online entirely through thought. Another breakthrough came from the University of Pittsburgh in 2016, when researchers developed a system that could restore the sense of touch. They implanted electrodes not just in the motor cortex, but also in the somatosensory cortex, the region responsible for feeling. When sensors on a robotic arm detected pressure, the system stimulated the brain in specific patterns, creating a perception of contact. The participant reported that it felt like their own hand was touching something again, even though the arm was robotic. That kind of closed-loop feedback marked a turning point, proving that BCIs could restore more than motion. They could restore feeling. In recent years, commercial companies have started turning these research prototypes into practical systems. Blackrock Neurotech, one of the largest running firms in the world, has implanted more than 30 patients with its Utah array, a device that can decode motor and sensory signals with remarkable precision. Some users have been able to play video games, draw shapes, or send text messages only using their thoughts. Another company, Synchron, has taken a different approach with a device called the electrode, which is implanted via the jugular vein instead of open brain surgery. Once in place, it expands into a mesh that interfaces with neurons in the motor cortex. Synchron's system has already allowed paralyzed patients to control smart home devices and communicate online, marking one of the first FDA-approved clinical trials for a fully implantable BCI. Beyond restoring lost function, brain chips are beginning to augment healthy brains as well. Neuralink, for example, has stated that its long-term vision goes beyond treating disease. While the company's first human trials are focused on restoring motor function for paralyzed patients, its engineers have suggested that future versions could one day enhance memory, help manage mental health disorders like depression or anxiety, or even link multiple brains to share information directly. Those ideas remain speculative, but they highlight the expanding ambition of the field. In the near term, the most transformative applications may involve neuroprosthetics, devices that directly connect to the nervous system to replace missing limbs, restore senses, or regulate brain activity. Cochlear implants, which have already restored hearing for hundreds of thousands of people, are one form of this concept. Retinal prosthetics aim to do the same for sight. Deep brain stimulation, which uses implanted electrodes to treat Parkinson's disease and severe depression, operates on similar principles, sending targeted pulses to modulate brain circuits. Even outside medicine, researchers are exploring experimental uses in gaming, virtual reality, and human-machine collaboration. Companies like NextMind, acquired by Snap Incorporated, have built non-invasive brain sensors that let users control digital interfaces with thought alone. Imagine playing a video game where aiming or movement responds instantly to your intent, no controller required. Or astronauts operating robotic systems on Mars using thought-based control when physical delay makes manual operation difficult. Those possibilities are still early, but the science behind them is already proven. The growing ecosystem of applications shows how versatile brain chips can be. Whether through restoring lost abilities, extending human control into machines, or merging cognition with digital systems, they're redefining what it means to interact with tech. The next challenge will be scaling these advances safely, affordably, and ethically, a topic that demands as much attention as the science itself. Brain chips are not just another gadget. They represent a fundamental shift in how humans interact with technology. For the first time, machines can directly interpret the language of thought, allowing intention itself to become an interface. What began as an effort to help thoughts and paralyzed patients move again has evolved into a glimpse of the future where the boundaries between mind and machine begin to dissolve. But that future comes with questions about privacy, identity, and what it means to enhance the brain rather than heal it. The science is advancing faster than the ethics can keep up, and the choices made now will shape how this tech is used for generations. Whether brain chips remain tools of restoration or become extensions of human potential, one thing is clear. The power to connect thought and technology is no longer science fiction. It's already happening.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.